Hi everyone, in this video I'm going to cover chapter 14.4 page 15 that I did not cover in the previous video. From what we learned in the previous video, we learned how to find out pH from the concentration of proton or hydronium ions by take negative log to it. Again, P scale is the negative log scale. So this P right here is the same as negative log. So that means whenever you take negative log of something, it's going to be P of that thing. For example, if you take negative log of X, you can call this as Px, for example. In this video, we are going to do the reverse process of it. We are going to take a look at what happens if we obtain the pH. How can we convert that to the concentration? In order to do this, we are going to use the concentration of proton will equal to 10 to negative pH. For example, as you see here, the given pH equal to 4, so the concentration would equal to 10 to negative pH, which is negative 4.00, which is equal to 1.0 times 10 to negative 4. Because this is the concentration, it needs to come with the unit, and the unit of concentration is in molar. Now let's take a look at the significant figures. Before we learn that going from the concentration to the pH, right? For example, concentration of proton to the pH, what we can do with the sig fig is that the number of significant figure in the concentration will become the number of decimal place in the pH value. Vice versa, if we do the reverse process, that means the number of decimal place of the pH must become the number of sig fig in the concentration. If you look at the pH value contains 2 decimal places. So that means the answer of the concentration need to contain 2 significant figures. Let's take a look at the next pH value, 10.85. If you do the same thing to find out the concentration of proton for the pH 10.85 by doing negative 10 raised to negative 10.85, you are going to get the value of 1.4 times 10 to negative 11 molar. Again, 2 decimal place from the pH, then will become 2 sig fig for the concentration. Let's continue to the next one. The next one is the pH of negative 0.21. So in this case, you are going to do 10 to negative, and don't forget the negative of 0.21. You are going to get the concentration of 1.6 molar. As I mentioned earlier, you can see that the higher concentration will associate with the low value of the pH, and to have a negative value of the pH, it is okay. And as you see here, because the pH of the solution equal to 4 indicate that this solution is acidic solution. This is the main reason why the concentration of proton is a high value, higher than 10 to negative 7, which is the concentration of proton of the pure water. So again, the concentration of proton in pure water is equal to 10 to negative 7 molar. And as you see, the concentration of pH, the concentration of proton of pH 4 is greater than of in pure water, so that's indicate acidic solution. Now, if you're looking at pH of 10.85, this indicates pH of the basic solution. And as you see, the concentration of proton is actually a lot lower than 10 to negative 7, which is of pure water. Again, because pure water contains both proton and hydroxide ions, so that means the amount of these two, the relative amount of these two will tell you the type of the solution. What do I mean by that? For example, if in pure water, these are the amount of these two, right? But if you in a solution, if you end up with a higher number of proton than the hydroxide ions, then that solution would be acidic because it contains more acidic proton. However, if you have a solution that contains more of the hydroxide ion than the proton, then that solution would be a basic solution. Same thing for the last pH, right? So this last pH is a very, very low pH. So that's why the concentration of proton come out to be a really high, a lot higher than the concentration of proton in pure water. We can also apply the same p scale with the concentration of hydroxide ions. As I mentioned earlier, whenever you take negative log of something, it's going to become p of that thing. For example, if you take negative log of proton, then it's going to become pH. If you take negative log of x, then it will become px. So that means if you take negative log of OH, then it's going to become POH. So you will see, you will get to use this equation quite often for this chapter. And same thing to do the anti-log, we are going to do this. We are going to use the same idea that we did with the proton. So in order to get the concentration of hydroxide from the POH, you are going to do 10 to negative POH. Now let's practice example 3 and 4 with this concept, and pause the video for that and resume it again when you're done. Let's take a look at example 3. Calculate pOH of the following concentration of hydroxide ions. pOH of the concentration of hydroxide ion equal to 1.74. If you take negative log of this value, you are going to get pOH of negative 0.241. Again, again, the number of sig fig for the concentration then will become number of decimal place in the answer. So since this concentration contains 3 sig fig, the answer for the pOH would contain 3 decimal place. Vice versa, if you're going from the pOH to OH, then it's going to, the rule will be the opposite. Okay. Next, let's take a look at the next example, which is 0.005 millimolar. This M right here is milli, is mean 10 to negative 3. So that means you will need to convert this concentration into just molar by multiply this or divide by 1000, but it's the same idea. If you do this, you will get the answer equal to 4.26. Again, if you're going from the concentration to the pH or pOH in this case, you're gonna use sig fig and translate that to the decimal places. So in this case, you are going to see that we have 2 significant figure from the concentration. That means the final answer would contain 2 decimal places. Okay. Now let's take a look at example 4. Example 4, we are going to do the reverse process. The concentration of hydroxide ion would equal to 10 to negative pOH. So that means if you do 10 to negative 2.50, the concentration of pOH for this the concentration of the hydroxide ions for this pH would equal to 3.2 times 10 to negative 3. Again, don't forget the concentration, which is in the unit of molarity. And to consider the significant figures, we are changing from pOH, which means you're going to look at the number of decimal place. And since there are 2 of them, so that's why your final answer will also contain 2 sig fig. Okay, so because the opposite, right? Next, if you do 10 to negative 8.23, you will get 6.0 times 10 to negative 9 molar concentration. And if you do 10 to negative 0.55, you're going to get 3.5 molar for this example. Now to summarize the sig fig rule, when going from pOH to concentration of hydroxide ions, you are using number of decimal place and convert that to number of sig fig. Vice versa, going from concentration of hydroxide ions, you are going to convert that into number of decimal place. For example, in this case, the decimal place is 2. That's why the significant figure will be 2. Vice versa, because this value contain 2 significant figures, that's why the value of pOH would contain 2 decimal places. From chapter 14.3, we learn about autoionization of water. We learned that the equilibrium concentration, the equilibrium constant of water ionization is equal to 10 to negative 14 at 25 degrees Celsius. Again, this relationship only apply at 25 degrees Celsius. Anything outside 25 degrees Celsius, you will need to use a different different way to derive it. So if you think about this, because Kw equal to 10 to negative 14, that means for water, the concentration of proton would equal to 10 to negative 7, which I mentioned earlier, and concentration of pure water for hydroxide ion would equal to 10 to negative 7 for pure water at 25 degrees Celsius. So if you take negative log of this Kw value, this is what you will get, is the pH plus pOH equal to 14. Okay, so again, this relationship apply to only at 25 degrees Celsius. Any temperature outside these 25 degrees Celsius, it will not work. Okay, so that means if you're looking at the this relationship here, you will see that the pH and pOH are inversely related to each other, and they both are constrained by the 14, which means if the pH is high, the pOH have to be low. Vice versa, if you have a high pOH, then the pH of the solution will be low because constrained by this 14. So now let's take a look at how can we find out pH from the given pOH. So pretty much, as I mentioned before, this example given us at 25 degrees Celsius. So that means this relationship that we just talked about will apply. So in order to find out pH, you will use 14 minus pOH, which is 2.5, and you will get the value of 11.50. The high pH indicate that this solution is a basic solution, higher than 7, which makes sense because for basic solution, the pOH have to be lower than 7, but the pH have to be greater than 7. So that makes sense, right? Because they are inversely related. Now move on to the next. If you do the same thing, subtract 8.23 from the 14, you will get 5.77. Next, if you subtract negative 0.55 out of 14, you will get 14.55. So that means the pH and pOH it can be beyond the 14 and below 0. As long as those two add up together equal to 14, it should be fine. Right? So the negative will not play any role in this because it just tells you that it's a very, very basic solution. And as you see from the pH as well, the pH is out of scale because it's very basic. As long as these two add up together equal to 14, this is still reasonable. Now let's take a look at example 6. Example 6 asks to find out the concentration of hydroxide ion, but it's given us the pH value, and the keyword for this is 25 degrees Celsius. So what we know about 25 degrees Celsius is, again, we know that pH plus pOH equal to 14. Okay, so that's what we know. Now, if you do 10 to, because we want to find out concentration of hydroxide ions, but it's giving pH, so that means if I do 10 to negative pH, which is equal to 10 to negative 2.45, the answer for this will not equal to the concentration of hydroxide ion, but it will equal to the concentration of proton instead, because you do 10 to negative pH, and pH and proton are related. Therefore, we need to find out pOH because pOH is related directly to the concentration of hydroxide ions. So that means in this case, we need to find out the concentration of pOH from this relation at 25 degrees Celsius, which pOH equal to 14 minus pH. You are going to get 14 minus 2.45, which is equal to 11.55. Okay, indicate that this solution is acidic because pH is below 7, but pOH is greater than 7. Then you can find out the concentration of hydroxide ion by using 10 to negative POH, which is equal to 10 to negative 11.55, and that should come out equal to 2.8 times 10 to negative 12. And don't forget the unit is in molar. Next, let's check the significant figures for this answer. So at the beginning, we subtract 14.00 from by 2.45. You see that these two are subtractions, so we're going to go by the number of the least decimal place. So your final answer for 11.55 should contain 2 decimal places. Next, going from POH to the concentration, we are going to convert number of decimal places to the significant figures. So we have 2 decimal places from 11.55. Therefore, our final answer should contain 2 significant figures. So that means this is the correct answer for this problem. Please watch the rest of chapter 14.4 in the previous video that I provide. Thank you for watching.